Good day. Welcome to the fourth lesson in the series. In this lesson, I present a new method for factorizing quadratic expressions. I have called this method the compact method, and I'm calling it new because this is something I have come up with, and thus far I have not found anything similar to it on the internet. Factorizing can be used outside of the context of solving equations. So, although this lesson is part of a series on solving quadratic equations, I will focus on factorizing and stop short of solving any equation that the quadratic expression might be associated with. I think you will manage that final step fairly easily. The quadratic formula for solving quadratic equations will be presented in a later lesson. That formula will probably be a better method than the one shown in this lesson to solve a quadratic equation that is difficult or impossible to factorize. But if instead you are having difficulty factorizing a quadratic expression within an algebraic fraction, then this compact method might be helpful. A previous lesson introduced concepts and jargon that I will use in this lesson. If any of it is unfamiliar to you, please go back to lesson 2 for a fuller explanation. The method I am introducing in this lesson is probably appropriate for situations in which the coefficient of x squared is bigger than 1. There's no particular advantage in using it when the coefficient of x squared is equal to 1. In the lesson, I will use the same examples as used in previous lessons. They are smallish classroom type examples, and they are suitable then for demonstrating the techniques of the method. Once that is established, I will show the method being used in bigger examples in which the trial and error methods might not get to a solution easily. The benefits of this method are that it is methodical as compared to trial and error, and it is efficient in the sense that it is able to exclude combinations that need not be considered. Situations in which we would need to factorize are solving equations. In simplifying algebraic fractions, there's no equation involved, but factors in the numerator and denominator can be eliminated and thereby simplifying the fraction. One bit of jargon that I use is the word FOIL. It is a memory aid to help students remember what to do when distributing multiplications across brackets. In particular, the word outers and inners is what I will use frequently in the description. The method works slightly differently for the situation where the constant term is positive and when it is negative. When the third term is positive, the factorizing patterns that we use are two pairs of brackets in which the sign of the middle term is the same, either both of them plus or both of them minus, and whether it is plus or minus is determined by the sign of the middle term in the original expression, the term containing x. In this example, the coefficient of x squared is 15 and the constant term is 6. So the factors of 15 are going to appear with x in the first pair of brackets AND with X in the second pair of brackets. And similarly, the factors of 6 will appear as the N bit in each pair of brackets. The sign involved will be plus because of the plus in front of the 19. So the inners and outers in the jargon I mentioned earlier are both going to be positive, and they are going to add up to 19. To start off with the method, I set up a table with the factors of 15 associated with the rows and the factors of 6 associated with the columns, and in each case arrange them in ascending order. The rest of the table is formed by multiplying the factors of 15 with the factors of 6. Because of the way we've arranged the initial factors, the multiples will also increase from top to bottom and from left to right. And if we focus on what we are aiming for, the target of 19, we are going to be adding up these multiples of the factors. And if any of the cells is already bigger than 19, there's no other cell that will be able to pair with it to make 19 because all these numbers are positive. So all those cells that are grayed out are unnecessary. And that's the first bit of efficiency introduced by the method. So this is really our starting point for the method. Those grayed out cells will not ever be considered. I'll start by considering 15, and we'll see why in a minute. To make up 19, I'm going to need the number 4 to go with 15. But there is no such number in the body of the table. So I can exclude 15 from further consideration. I can also exclude it wherever it occurs in this table. Notice now that the entire row associated with the factor 15 has been depleted of all its options. So I don't need to consider it any further. But because the factor of 15 is paired with the factor 1, I can also remove that entire row associated with 1. Next, I can look at 18. To get 19, I need to add 1 to it. Unfortunately, there is no 1 in the table, so 18 will not be used. This time I've depleted the column associated with 6, and therefore I can also remove the column associated with 1. And now it becomes fairly easy, fairly obvious that the pair I need to consider are 10 and 9. They will give me 19. Once my decision is to use 10 and 9, I can use the numbers that make up 10 and 9 to put into the factorising pattern. Remember, we said that the factors of 15 are going to be associated with x. In this case, it is 5 that was the factor of 15. So that goes with x, and 2 was a factor of 6. So that goes in the position shown in the bracket. It has to be multiplied with a 5x. For the other choice we've made, the 3 shown in red was a factor of 15. So that's going to go into the slot with an x. And the 3, the blue 3, was a factor of 6. So that goes into the slot shown there. And we factorized the expression, whether it's going into an equation or into an algebraic fraction. When the coefficient of the middle term is negative, the method works in a very similar way by just focusing on the absolute values instead. When we do the adding up, the factorizing pattern we've used with minuses as shown will ensure that the result we get is negative. But in building up, we can just consider the equivalent absolute values. So instead of looking at a target of minus 11, we know we're looking for 11. This time, I'm going to use factors of 6 down the rows, coming from the coefficient of x squared, the factors of 3 along the columns, coming from the constant term. The cell grayed out, the cell with 18 in it, comes from 6 multiplied by 3, and because that is bigger than the absolute value, 11, we know we will never be able to get to a total of 11 using 18. So that's going to be excluded. So now this is my real starting point without the 18 shown. I could choose any number, but as we saw, there's some advantage in choosing a row or column that is almost depleted. So to get to 11 from 6, I'm going to need 5. There is no 5, so I can exclude 6 and also the other 6 where it occurs. Now that bottom row has been depleted, I can remove it, and the row it is associated with can also be removed. Okay, because if I'm not using the factor 6, I cannot use factor 1. I can now consider 9 and 2. And they are going to give me a total of 11. Now, putting it into the pattern, a pattern, remember, now has a negative sign in each pair of brackets. And still, we're going to use the factors of 6 to go into the slot with x. So the 2 is a factor of 6, so that's going into a slot with x, and the 1 was a factor of 3, so that's where it goes into the pattern. Notice it has a minus in front of it. The other one, the 3 and the 3, again, the 3 is a factor of 6, goes into a slot with x, and the other 3 goes into a slot that will generate the constant term. And notice that it is also associated with a minus sign. So the 2 minus signs are going to get me a positive 3. There it is solved. So that was just the smallish examples to demonstrate the method. And now I'm going to show it with some bigger examples that might be difficult to solve in a conventional way. Before we get into it, just be aware of the rules that are going to apply. We've seen that there are some situations in which a cell would be unnecessary. And as soon as you have established that one cell is unnecessary, then all the cells to its right and all the cells below it, which form a block, all of those cells can be excluded. For the situation where the third term is positive and also when it is negative, which we will come to in a while, the choices that we make must come from different rows because those rows are associated with factors of the term in x squared. And also those rows must share a paired factor. Similarly, the choices we make must be from different columns, and those columns must share paired factors, which would be paired factors of the constant term. Sometimes it is not possible to pair factors, and this happens when the coefficient of x squared or the constant term has an odd number of factors, or equivalently if they are square numbers. In this example, 9 is a square number, so when we factorize it, you'll see that 3 is not paired with anything. Similarly, 16 is a square number, and it is not paired with anything. When that happens, just duplicate the row or the column as necessary. So here to a biggish example, 18x squared plus 39x plus 20. So in the method, we're going to arrange the factors of 18 down the rows and the factors of 20 along the columns. Some of the cells, they are grayed out because they would have been values bigger than 39, our target. So there's no need to consider them. Our starting point is now as shown. So we could start with 20, noting that that column is almost completely depleted. To get to 39, I'm going to need 19 to pair with 20, and it's not available. So I can eliminate 20 wherever it occurs. Now that column of 20 can be removed. There's nothing else in it to use. And consequently, the column associated with 1 can also be removed. Then I could consider 36. To get to 39, I need to pair it with a 3. There is no 3, so 36 can be removed wherever it occurs. Now, the row associated with 18 has been depleted, so I can remove that row and also the paired row of 18. In other words, the row with 1. Now I can consider 30. I need 9 to pair with it to get 39. There is no 9. I can remove 30 wherever it occurs. And now the column associated with 10 cannot be used at all. There's nothing in there that I can use. And also the column paired with 10 can also be removed. What has also happened now is that the row associated with 9 can be removed, and therefore the row associated with 2. The method indicates what combinations need not be considered. Now I can consider 24, which needs 15 to make up 39, and indeed there is a 15. As before, we now transfer the pairs we've found into the factorising pattern, which has a plus sign in each pair of brackets. The factors of 18 are going to go into the first part of those brackets. So the 6, which was part of the 24, will be associated with an x, and the 4 with the n part that's going to be part of the constant term. The other choice we've made, 15, is made up of 3 and 5. 3 goes into the slot associated with x, and the 5 into the constant part. And there we have factorized the quadratic expression. The situation where we have a minus, remember, we are just going to consider the absolute value to start off with. Our pattern is going to have a minus and a minus in there, but we will consider the target as though it were 83 instead of negative 83. I've arranged the factors of 40 down the rows and the factors of 42 along the columns. Notice that several of those cells are unnecessary because when we multiply, for example, 2 with 42, we're going to get 84. And that's bigger than our absolute target of 83. So there is our starting situation. If I choose 42, then I'm going to need a 41 with 42 to make up 83. And there is no such number in our grid. So I will delete 42 wherever it occurs. The column associated with 42 is now empty. I can remove it, and therefore all the cells in the column associated with 1. I can now consider 80, and it needs a 3 to make up 83. Aha, there is a 80 and a 3, but notice that 80 and 3 are in the columns associated with factors 2 and 3, but they are not paired factors of 42. We cannot use this combination. I can remove 80 and 3 because they are paired only with each other and nothing else. The row for 40 is now depleted, so I can remove it, and therefore also the row associated with 1. Notice also that the column associated with 21 can now be removed, and therefore the column associated with 2, the paired factor of 21, that can also be removed. Let's try another cell in the table, 60. 60 would need 23 to make up 83. There is no 23, so I can remove 60 wherever it occurs. And the row associated with the factor 20 can be removed, and therefore the row associated with the paired factor 2 can also be removed. Another cell I could try is 70. I need 13 to make up 83. It doesn't exist. I delete it. I delete the other 70. Try another pair, 56 and 27. 27 doesn't exist, so I can remove 56 and 56. And now the column associated with 14 can be removed, and also the paired column. 14 and 3 were paired factors of 42. So 3 can also disappear. The row associated with 10 is now depleted. I can remove that. And also the row associated with 4, because 10 and 4 were paired factors of 40. Try 48. I need 35, and there it is. I've got pairs that are going to add up to 83. Now we can transfer our choices into our factorising pattern, which has a negative sign in each pair of brackets. Remember, the factors of 40 are going to go into the slot associated with x, and eventually to generate the term in x squared. And the factors of 42 are associated with so 48, made up of 8 and 6, are going into the slot shown. And the factors of 35 are going into the slots shown there. And we have factorized that situation. So that covers situations in which the third term is positive. Let's have a look now at when the third term is negative. As before, I will use small examples just to demonstrate the method, and then bigger examples to show some unusual situations that could arise. When the third term is negative, the constant term is negative, our factorizing pattern will be 2 lots brackets and a different sign in each of them. This sign in the starting expression doesn't really help us in knowing immediately where to use the plus or the minus. The rules are very similar to the situation in which the third term was positive, except that when the third term is negative, the rule about excluding all cells to the right and all cells below some point no longer applies. But all the other rules still do apply. For this example, in which the constant term is negative, our factorizing pattern involves 2 pairs of brackets one of which has a plus sign in it and the other has a minus sign. So when we do the multiplications that generate the middle term, one of them is going to be a positive piece and one of them is going to be a negative piece. And we are going to try to combine them in such a way as to get a positive 7x. So that is our target. And the pieces building up to the target are going to involve a positive piece and a negative piece. To get to a positive result, we need to have a calculation in which a big number minus a small number is involved. That will get us a positive value. I could rearrange that conceptual equation into saying that the big number will be the small number plus 7. So I can always start with some small number and calculate the associated big number. Alternatively, I could start with rearranging that little equation to be small equals big minus 7. So I would start off with a big number and calculate a small number. I'm going to demonstrate the two ways, but in practice, I would just use one of the ways. So using the little formula that big equals small plus 7, I would start with 1. 1 plus 7 is 8. So big is should be 8. There is no 8. I can exclude 1. Next choice is 2. And the paired number with it would have to be 9. Notice that in this use of the method, we can't jump around as we did when we had a positive constant term. We have to choose the smallest number, whichever it is. The next smallest number is 3, and 3 plus 7 would be 10. And there is a 10, but these choices are not associated with paired factors of 20. So I can remove the 3, but I cannot remove the 10, because although 10 cannot be used as the big number, it might be a valid choice for a small number later in the process for a different example. So I cannot remove the 10. I've managed now to deplete the column for 1, and therefore I can remove the column for 20. The next smallest number is 4, and 4 plus 7 is 11, but there's no 11, so I will exclude 4. The next one is 5, and 5 plus 7 is 12, and indeed there is a 12. So that would be the pairs that I would use for this factorizing. Just for demonstration, I will look at starting with a big value and calculating a small value. So the biggest value is 60. So the small value based on that would be 53. Doesn't exist, so 60 can go. The next smallest is 30. Needs 23, which does not exist, so 30 cannot be used. Next one, 20. 13 is needed, but there is no 13. So I will delete 20, and I can now remove that column for 20, and therefore the column for 1. The next available big number is 15, and that needs 15 minus 7, it needs 8. It doesn't exist, so I will eliminate 15. The next biggest number is 12, and the associated small number would be 5. And using this approach to the method, I get to the same pair that I found in the previous way. Now I can take those values, slot them into our pattern. Notice that we still don't know yet which one is going to be plus and minus, but we know where they should go. The red 3, which is a factor of 3, is going to go into the slot associated with x. 4 is a factor of 20, so that's going to go into the position at the end of the brackets. The other choice, the 1, is going with the position for x, and the 5 with the position for the constant term. Now, in order to get a positive 7, remember that we needed a big number to be positive, to get a big minus small to result in 7. And here 12 compared to 5 is big. So the pair that makes up 12, that must be giving me a positive value. And the pair that gives me the 12 is 3 and 4. So the 3 and 4 is what's going to determine which gets the plus. So 4 must get the plus. 3 is already restricted to be plus in terms of our pattern. And because the second bracket is getting the plus, the other one must get the minus. And we have factorized it. An example where the middle term is minus. Let's see how that one works. So now to get a minus value, a negative value, I need to have the calculation in the other order. Small minus big, that is what would give me negative. So rearranging the conceptual equation to see that big will be equal to small plus 4. I can choose the small value and from it calculate the big value. Of course, there is the other way, but I'm not going to use that one. I would take a big value and do big minus 4 to get the small value. So using the first way, starting with a small value of 1, I see that the big value should be 1 plus 4 equals 5. 1 and 5 do exist, but because they are in the same column, I cannot use them. So I can eliminate 1, but as I described earlier, I cannot eliminate the 5. Next one to consider is 2. That's the next smallest number, now that 1 has been excluded. But although 6 is available, I can't use it because they are in the same row. So I will eliminate the 2, but I cannot eliminate 6. Next one to consider, 3 plus 4 is 7. There's no 7, so I cannot use the 3. Next one to consider, 4 is then 8. No, so I can't use 4. 5 is there 9? No. So the column associated with 1 can be removed, and therefore the column associated with 12. Next to consider, 6. 6 plus 4 would give me 10, and indeed there is a matching 10 that I can use. Now that I have them, they can be slotted into the factorizing pattern, as can the other pair. Now, for this situation where we wanted a minus, effectively the big number needs to be negative. The big number of 10, which is made up of 5 and 2, that is what will determine where the sign goes. So 5, because of our pattern, has to be positive. So the 2 is made negative, so that we end up with a minus 10. That's what we wanted. The 10, the big number, to be negative, because the second bracket has the minus, the other one has to have the plus. Right, so that's the method shown, and let's use some big examples to test it. Because the constant term is negative, the factorising pattern is going to have plus in the one and minus in the other. And the factors of 25 are going to be associated with x. The factors of 36 are going to be in the constant term position. I've arranged the factors of 25 down the rows, the factors of 36 along the column, and notice that I needed to duplicate the column for 6 and also the column for 5. Because I need a positive value in the middle term, I'm going to need a big number minus a small number to get a positive value. And rearranging to see how I would get to the big value by using the small value, I say that big equals small plus 25. There is the other possibility, but I'm not going to use it. So just to speed matters up, I've put a few of them together. I would have considered 1 and then 2 and then 3 and then 4, and each of their necessary partners are not available. So I would eliminate 1, 2, 3, and 4. The next smallest number available is 5. There is a partner 30 for it, but for various reasons I cannot use them. The ones with a line through them now cannot be used because they are in the same row as the 5 that I'm considering. The 2 in the bottom, they cannot be considered because they are in the columns associated with 6, and 5 is in the column associated with 1. And 1 and 6 are not paired factors of 36. So I will eliminate 5. The next few to consider are as shown there, and because their partners are not available, I'm going to eliminate 6, 9, 10, 12, 15, and 18. Now, the next smallest available number is 20, and that needs to be paired with a 45. And indeed, there are 2 45s. Let's see what we can do with them. The first one cannot be used because it is in the same row as the 20, but the bottom one I can use. So now I've got the necessary combinations, and they can go into the factorizing patterns as shown. To decide about the sign, remember we need a positive sign, so it's going to turn out that the big number must be positive. The numbers making up 45 rather than the numbers making up the 20. So I need the 9 to be positive in addition to the 5 there. And because we've determined the 1 has been positive, the sign in the other bracket must be negative. The last one to consider is where the middle term is negative. So our target of negative 25 is going to need a small value minus a big value. We see that to get to a big value, then we would need to calculate it as the small value plus 25. Again, we could start working with the big values, but that is a bit more tedious. I would consider in sequence 1, 2, 3, and 4, just to speed the lesson up a bit. Their partners of 26, 27, etc. are not there, so 1, 2, 3, and 4 can be excluded. The next one is 5. 5 is paired with 30, but they are not in columns associated with paired factors of 12. 5 is with 5, and 30 is with 10. The next few to consider in sequence, and again, I'm only showing them all together just to speed up the lesson. But 6, 8, 10, and 12 can be eliminated because their partners of 31, 33, etc. are not available. And now I've got to that situation I like, where we can eliminate one column and therefore a second column. The next smallest number now is 15 to be considered with 40. And indeed, there is a 40 in an acceptable position. And as we've seen before, they can go into specific slots determined by our factorising pattern. Also the numbers in the second of those pairs. Determining the sign now, we need a negative sign, so our big number effectively must be negative. We're going to have small minus a big. That minus in front of the big indicates that the 40 rather than the 15 must be negative, and the 40 is made up of the 4 and 10. So those are going to determine the negative combination. And once the negative is determined, the other one must be positive. And so we have managed to factorize this expression as well. Just as a quick, rough, non-scientific way of demonstrating the efficiency of these methods, here's a biggish example when simplifying fractions. The numerator had 60 pairs of numbers to consider, and the method is able to find the necessary factors by considering only 4 pairs. The denominator, which because it has a minus in the middle term, works a bit less efficiently, but the denominator had 72 pairs to consider, but the method only needed to consider 18 pairs. In the examples we have gone through, the pairs that needed to be considered and the pairs that are actually considered are shown. And it gives some very rough idea of how efficient it is relative to the conventional trial and error methods. I hope you find this method useful, and I look forward to seeing you in the remaining lessons in this series. Bye for now. See you again.